Hello dear children, welcome to another episode of Blast from the Past, where we will be discussing previous year questions from JEE Advanced. So today I have selected a question from JEE Advanced 2017. It is a question from System of Particles. So let us see the question. So here there is a block of mass capital M. It is resting on a frictionless surface. It is resting on a smooth surface. A cut is made, a circular cut is made in this block, and a point mass is kept at the top, at this top edge, right? And the entire system is released from rest. We are also given that this surface is also frictionless. So both the surfaces involved are frictionless. Right. So now we are asked to evaluate various options. Now this is a multi-correct question. We have different options. We have to check the velocity of the point mass at the lowest point, the displacement of the bigger block, the velocity of the bigger block, and the position of the mass, right? So how to approach this question? So in this question, certain key concepts are involved. The first and most important concept is that since the entire system, right, I can take the system as this big block plus the point mass. So if I take these two as the system, then the system is resting on a frictionless surface. So now let us analyze the forces on this system. So can I say that there is no external force on the system in the horizontal direction, right? Since the surface is frictionless, there is no horizontal force, no external horizontal force on the system. So then I can conserve linear momentum in the horizontal direction. There is in the vertical direction, momentum cannot be conserved because of the presence of gravity as a gravitational force as an external force. But in the horizontal direction, I can conserve linear momentum, right? So I'm writing for horizontal direction, F external is equal to 0. So whatever momentum, right? Whatever momentum was there initially in the horizontal direction, that has to be conserved. What is the momentum in the horizontal direction? Initially, we have taken this entire system to be at rest. So there is no initial momentum in the horizontal direction, right? Now we are concerned with the lowest point, that is when the point mass reaches the lowest point, right? Suppose it is moving with a velocity small v to the right, okay? So this capital M, this bigger block, has to move to the left. Only then we can say that the momentum will be conserved, right? Momentum in the horizontal direction has to be conserved. So since F external is equal to 0 and P initial is equal to 0, P final, which is the vector sum of momentum of the small mass plus momentum of the bigger mass, should also be equal to 0. So if I consider only the magnitude, I can say that M into small v is equal to capital M into capital V, right? So this is one important conclusion that we can draw from this situation. Another conclusion that we can draw from this about the position of the center of mass, right? So since F external in the x direction, in the horizontal direction, is equal to 0, I can say that the velocity of the center of mass in the x direction should remain unchanged, right? Velocity of the center of mass in the x direction cannot be changed. Now initially that is 0, so finally also that should be 0. So if I write that vectorially, This is mv vector plus capital M into capital V vector by m plus m, right? So since the center of mass was initially at rest, the center of mass should continue to be at rest along the x-axis, the position coordinate of the center of mass. The x coordinate of the center of mass cannot be displaced. So this is another important conclusion that we can draw from this situation. So the x coordinate of the center of mass remains unchanged. So let us use these two concepts and proceed further with the problem. So how can we use this idea to conclude or to find out how much the block will be displaced? That is, if the small point mass reaches the lowermost point, how much should the bigger block move backwards so that overall the center of mass or the x coordinate of the center of mass remains unchanged. So to find out that, you should know an important result. So that is regarding how center of mass divides the line joining a two particle system, right? What is the ratio in which the distance between 2 point masses is divided by the center of mass. So to find that out, we will assume the origin here. So we keep m1 at the origin and the distance between m1 and m2 is d. So what is the coordinate of center of mass? Coordinate of the center of mass can be calculated as m1 into 0 plus m2 into d by m1 plus m2, right? That is, this distance is equal to m2d by m1 plus m2. So what will this distance be equal to? This distance will be equal to d minus m2d by m1 plus m2. That is nothing but m1d by m1 plus m2. So are you seeing an interesting fact here? If I multiply m1 with its distance from the center of mass, that is, if I multiply m1 into its distance from center of mass, what is its distance from center of mass? That is m2d by m1 plus m2, right? This product is equal to m2 into its distance from center of mass, right? m2 into its distance from the center of mass is m1d by m1 plus m2. So this product will always be equal. I can always say that m1 into OC is equal to m2 into CP, provided the center of mass remains unchanged, right? So this is the second key point that we are going to use. Now from this I can say that if I move small m1, if I move m1 to the right by say delta x1, I can find out by what displacement I have to, by what quantity I have to displace m2 so that the center of mass does not change. So if the center of mass does not change, then the new distances will also obey this law. The new distances will be m1 into OC minus delta x1. That will be equal to m2 into CP minus delta x2. So the new distances will also follow this, right? So I can just cancel off OC. What I'll get is m1 delta x1 is equal to m2 delta x2. So in order for the center of mass location to be constant, center of mass location to be unchanged, if we move one mass towards the center of mass by delta x1, then the other mass has to be moved by delta x2 in such a way that m1 delta x1 is equal to m2 delta x2. All the difference or the movements have to be made in the inverse ratio of the masses, right? Movement have to be made in the inverse ratio of masses. So this key concept we are going to use to find out the location of I mean, how much the block will be displaced with respect to the points. So using this concept, we can proceed with the problem. So now I have to assume, right? I am assuming that when the point mass slides down and reaches the lowermost point, when it reaches the lowermost point, it has been displaced by r, but this displacement r is with respect to the bigger block. So with respect to the bigger block, the smaller point mass has been displaced to the right by r. But we know that the bigger block would have been displaced, say, by x to the left, right? So when we observe from a ground frame, with respect to ground, how much would the point mass have traveled to the right? It won't be r, right? It will be r minus x. So I am using the previous concept. So if the point mass has been displaced by r minus x with respect to ground, r minus x with respect to the ground, then the bigger mass, this block, should have been displaced. We have assumed this x. This is with respect to ground. So I can equate these two products, right? That is what we saw in the previous concept. The distance between center of mass and the masses, individual masses in a two-particle system, vary as the inverse ratio of the masses. So I can equate these products. From this, if I rearrange, I'll get x is equal to mr by m plus m, right? This is what I'll get. So the minus sign in the option will come because we have taken, so for them, they have taken the axis like this. This is the positive x-axis, this is the positive y-axis. We have taken x positive as along the negative direction. So considering the sign, the x component of displacement of the center of mass of the block, that is how much the block has been displaced, is given by minus mr by m plus n, right? Now coming to the second part, we have to also find out the velocity. Yes, velocity of the point mass when it reaches the lowermost point. For this, we will apply work energy theorem or the conservation of energy, right? So when the point mass reaches the lowermost point, it would have lost, how much potential energy is lost in this process? Right, mgr is lost. This mgr will be converted into the kinetic energy of the system, right? So what mistake we usually make is we forget to take or include the kinetic energy of this big block, because this is also recoiling to the left. So we have to take the kinetic energy of the point mass and the bigger block, right? And to do that, we can use the earlier derived result. In the system, we had already derived that m small v is equal to capital M into V is equal to P, right? Their respective momenta will be equal. The momentum of the point mass to the right has to be numerically equal to the momentum of the block to the left. So let us use that. So this potential energy is equal to kinetic energies of the block and the point mass. So I am directly writing them as P square by 2 small m plus P square by 2 capital M, right? Now individual velocities have been asked. You just need to find out P from this equation and divide by the respective masses. You will get the velocities, and these velocities will be from the ground frame. So rearranging this, we can directly write P is equal to root of 2 one m will be outside, 2 mgr by m plus m. So this is the magnitude of the momentum, right? Magnitude of momentum we have got. Now from this, if I divide by m, I will get small v. If I divide by small m, so that will be root of 2gr. Now if we see the options, they have divided this, they have brought this m to the denominator, right? So this will be 1 plus m by m. So this option is also correct. Similarly, you can check the other options, right? This position of the center of mass, if we check, it will be not correct. The velocity of the block is also given as wrong answer is given, right? Velocity of the bigger block should be, if you have got the momentum, you just divide by the bigger mass. You will get the velocity of the bigger block. So velocity of the bigger block should come out to be m by m root of 2 mgr by m plus m. So clearly this is not matching with. So we have two correct options. So an interesting observation in this question is that we could do all of this because the velocity of the point mass while just leaving the block has been asked, right? In that case, we know that the velocity is going to be completely horizontal. There is no Vy component, right? There is no vertical component. If we were asked to find out the velocity somewhere here, we will not be able to apply all of this, right? Then there will be a Vy component for a vertical component for the velocity. Then the process will be more complicated. But we can relate this momentum and energy like this only because the velocity at the lowermost point where it just loses contact with the block will be only in the horizontal direction, right? So that is one interesting observation that you should carry forward, right? Otherwise there will be a component, I mean in kinetic energy there will be a term like this. This will also have to be accounted for, right? So to sum up what we have done, we were using which concept did we use? First we used the concept that if the external force is 0, then we can conserve horizontal momentum. The next concept is, since the system started at rest and external force is 0, so velocity of the center of mass is 0 and the x coordinate of the center of mass has to remain unchanged. It cannot be changed. Then we used the concept of inverse division, right? Center of mass divides the line joining the masses in this ratio. So we use that, and then we used conservation of energy, right? So we will be bringing you more such questions. So stay tuned and follow our channel. Thank you.